Hey, hey, it's Dr. J. 3.5 today, the transformations of functions. So a transformation means to change a function by one of the following transformations. So there are four basic types. There is a vertical shift, up and down, a horizontal shift, left and right, a reflection. It's like a mirror image, flipping something upside down or flipping it sideways. Or a scalar. I guess you could say scalation or something. I'll just call them scalars. A scalar, we'll get to it later in this lesson, means to stretch or to compress the graph, shrink it down to a smaller size. Okay. You might want to review 3.1 before we begin and look at the very end of the lesson when I talked about the catalog of functions. So there were 8 what I called parent functions or mother functions that you'll need to know, or that you should know for this lesson. Now I'm going to cut you some slack, mainly because of time and because some of these functions are going to be covered again in other sections. So of the 8 parent functions that we learned about in 3.1, here are the ones that well, let me just list them all out. We have what's called the identity. We have the absolute value. We have the quadratic, the square root, the cubic, the cube root, the reciprocal, and the reciprocal squared. Now, of these 8, I want you to know 6 of them. Well, I want you to know all 8 of them, but in this particular section, I'm only going to cover the following 6. I'm going to cover these 3, absolute value, quadratic, and square root. And I'm going to cover these 3, the cubic, the cube root, and the reciprocal. For this, we're going to skip for now until we get to chapter 5. So we'll come back to that in chapter 5. The identity function was already covered in chapter 2. All of those word problems that we did, all of the graphs, the slope, the y-intercept, all of that stuff was already covered. So we're going to go ahead and omit those for today, and we'll just talk about these 6 mother functions that you need to know. I'm calling them functions because they are functions. They satisfy all the properties and principles of a function. I will only use the f of x notation or the g of x notation if it becomes necessary, or in the event that the problem dictates that I need to use that type of notation. Most of the time when I'm actually solving and evaluating and graphing and doing the stuff that we do in math, I typically just leave it as a y. It's just a lot easier to work with. Okay. So that's what we're going to be doing. So basically what we're going to do is we're going to take these 6 functions and we're going to apply the 4 different types of transformations. These are the different types of transformations to these basic functions. Let's start with my favorite, the quadratic, also known as the parabola. Okay, so we have example 1 here. So suppose y equals x squared. so known as the quadratic function, is changed or transformed. I often will use those words interchangeably. Hence the name transformations. By adding 3 as shown below here in red. Now, I'm not always going to write it in red, but just to sort of get the emphasis down. I'm going to ask you some questions. What value is affected? Yeah, and then what is the effect? All right, and you really have to be careful. You know, I often mix these words up. You'll say affect when you mean effect or vice versa. So in the homework and subsequent assignments, quizzes and tests and things, I'll make a big deal about the difference between affected and effected. Okay, and then we're going to draw the graph. We're actually going to draw 2 graphs. One of the original, which we often call the mother function, or some people call it the parent function. So we're going to go ahead and get started with that. So hopefully you've looked at the catalog of functions so that you have a good idea of what you're starting with, because we always start with the mother function. Probably not a bad idea to just memorize these tables. Keep in mind that these tables are not the only points on the graph. These are a subset of the larger domain. So I usually plot -2, -1, 0, 1, and 2 when I'm doing the quadratic function. Each mother function or each parent function has a different subset of the domain that we work with. Okay. Now in the previous lesson, I probably showed you, plugging in the values and such. You could just memorize the y's and the x's, but what I do is just memorize the x's. Right? You don't have to memorize the y's because the formula y equals x squared sort of encapsulates what the y values are going to be. This is your memory right here. This thing remembers for you. So you just take the x, you plug it in here, and you square it, and you get 4. Now, you probably will just incidentally end up memorizing it because you'll do this enough times. -1, you plug it into x squared, you get 1. Yeah, -1 times -1. 0, you plug it in, you get 0. 0 squared. 1, you plug it in, you get 1. And then 2, you plug it in, you get 4. Okay. Now we're going to do the transformation. All right, so this is the transformation. Transform or change. Yeah. Now, you got to be careful here. It says x squared plus 3, right? Remember, this column here is already x squared. Yeah. Y is x squared. Yeah, that's kind of what the equal sign, Equal sign can also be read as is. So y literally is x squared. So you are going to add 3 to all the y values. All right. So what is it affecting? It affects the y values. That's the affect. All right. So come over here and just simply, let me just erase that and just go +3, +3, +3, +3, +3. There is no effect on the x values. I like to, draw this arrow here. It's going through the transformation tunnel and it's coming out the new function. Yeah, this is our new one. Sometimes call it the offspring. It's the child or the offspring of the mother function. Notice the x values have not changed, so keep them exactly the same. And then now you have your new y value. So 4 plus 3 is 7. Sometimes you put these right next to each other, but I'm trying to use up my board here. So 1 plus 3 is 4. 0 plus 3 is 3. 1 plus 3 is 4 again, and then 4 plus 3 is 7 again. So this is your new transformation table. Okay. Now we're going to draw, so what is the effect? As we'll answer this now. The effect is seen in the graph. Right. I mean, sometimes you can see it here, right? You can see that all the y values, all the y values have gone up 3 units. Yeah. Look at all the y values. They moved up 3 units. But to actually see it, it's nice to draw the graph. Okay. Let's see. I'm going to have to do some erasing here. So let's go to... So we got the old function here. Here's the old function. So here's x and y. All right. Remember, y is x squared. I'm just going to mark off the subset of the domain that I use. So and that's 2, that's -2, that's 1, that's -1. Here's 0. 1, 2, 3, 4, 5. I don't really need to go that high, but let's just do it anyway. All right. When the graphs get more detailed or more complex, I might actually use the grid, the graphing board that I have, but for today, I'm not going to. All right, so let's start off. Make sure when you're doing this on your computer that you plot the vertex first. When you're doing it on paper, it really doesn't matter what you plot first, but on the computer, you must plot the vertex first. Okay. Another thing is you need to do the vertex plus 1 additional point. So this is what it would look like on your homework. They almost make it a little too easy for you. But the graphing has really come a long way since I've been teaching. So I'm not going to complain. It's better than it used to be. But so that would be all you would see on the computer. It would automatically connect those with the shape, which kind of gives it away. I like to plot all the points, so I'm going to go ahead and do all of them. There's -1 and +1. There's +1, +1, and then there's 2 and 4. All right, and again, the arrows, they're a little bit misleading. As we talked about earlier, this arrow is actually coming down. So, I mean, nobody ever does this, but this is a neat way to draw a parabola. This arrow is going down, and then that arrow is going up. You could also draw it without arrows, but you do want to make sure that it's clear, if you're drawing this on paper, that it does go on forever. So that's one of the reasons why we use the arrows. It sort of tells the reader, oh, I'm going on forever and ever. Okay. And then we have our new graph over here. The new graph is y equals x squared plus 3. And that's this table here. I'm going to need to erase it. I'll put it back in a second. So we got a x and y. Maybe I'll put it over here a little bit. There's your y-axis. Let's do 1, 2, 3, 4, 5, 6, 7. And for the x's, let's just do the same x's. 1, 2, -1, and -2. Right, I don't really need any values below, not in this particular graph, so there's really nothing down here. Just to remind you what the new graph was, because I just erased it, it was -2, -1, 0, 1, and 2. And then it was 7, 4, 3, 4, 7. All right, and again, you want to plot the vertex first. So the vertex is at 0, 3. Yeah. So x is 0 and y is 3. Okay, and then pick any other point besides the vertex. I usually just go with the first one as long as it fits. -2 and 7. So that's 7 right there, right? 3, 4, 5, 6, 7. Okay, now I'm going to do all of them. So -1 and 4, right about there. +1 and 4, and then +2 and 7. Okay, and so now you can see the effect. Vertical shift up 3 units. That's the effect. Yeah. The effect, it's affecting the y values. All right, so there you go. Example 1 with all the detail here. One last thing I might want to mention before we move on is the domain and range. One thing you want to keep in mind is this is not the domain. This is a subset of the domain. The domain is actually all real numbers from -infinity to infinity. Yeah. And that's the same for both of these. Both of these graphs have the same domain. Okay. Remember, when we draw a graph, we're just taking a snapshot. We're just looking at a sample of an entire domain. In theory, if you had an infinite amount of time, you could sit here and plot an infinite number of points, and this graph would just keep getting larger and larger and larger. It would actually appear to get smaller, though, because you'd be floating farther and farther away from the graph as the x-axis approaches infinity and -infinity, and so, it'd be like flying over a city, and it looks like it's shrinking. Okay, enough of that. Now the main thing, you could just memorize the domain. In fact, I would look at the catalog of functions, and as I go through the rest of chapter 3, I'll emphasize this a little bit more. Some of the functions, in particular the quadratic, the linear, the absolute value, the cubic, the cube root, in fact, most of the functions, the domain doesn't change. The domain always stays the same. We'll have some more details on the other functions in which the domain does change, in particular the square root and the reciprocal function. You can't memorize the domain because it's going to change in every example. All right, so now the range. The range is the y values, just the y values. So you're looking at the y-axis. The lowest point on the graph is 0, and it goes all the way up to infinity. Yeah, so the range is from 0 to infinity. That's what the arrows indicate, that it's going up forever. Over here, when you look at the range, it's starting at 3. Yeah, that's the lowest point on the graph. Y is 3. And again, it's going all the way to infinity. Yeah, they're going up forever and ever and ever. So 3 to infinity. Okay. Let me move that over here. And we'll move on to the next example. At this time, I would typically say, are there any questions? But since we're just getting started, you can always come see me on Zoom if you have any questions. Okay. Let's move on and do example 2. Let's try another one. Example 2. Suppose y equals the square root of x is changed or transformed by subtracting, I don't know, how about 2? Okay. So we've got minus 2. What is the effect? What does it affect? It affects the y values. That's the effect. The effect is it shifts or moves the graph down 2 units. So the graph is going to get pulled down 2 units. All right. This is what we call the mother or the parent. You're going to want to memorize all the parent functions. It's been a while since I filmed 3.1, but I'm not sure if I went all the way to 16. I sometimes go all the way to 16, but I rarely ever show that on the graph because it's hard to show. But I'll do it here just anyway. Okay. So we're using the mother graph. Remember, y is the square root of x. So the square root, I just do this in my head. You could do basic square roots in your head. When they get more complicated, you might need, a device or some calculator or some, mechanical way of doing it. But you could do all of these in your head. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. 9 is 3. And 16 is 4. And now we're going to affect the y value by subtracting 3 from all the y values. Why did I say 3? I still have the last example stuck in my head. That clearly says 2. Somebody almost got extra credit out there. I caught it. So I'm subtracting 2. It's going down 2 units. Notice the x values have not changed. You might also notice that there are no negative x values, not in the mother function. There could be negative y values because it's been shifted down. So 0 minus 2, that's negative 2. 1 minus 2, that's negative 1. 2 minus 2, that's 0. 3 minus 2, that's 1. And 4 minus 2 is 2. So this is the new graph, y equals square root of x minus 2. Or it's not the graph yet, it's the table. But I mean, if you have a table, making the graph should be relatively simple. All right. Here's my old graph. I'm not plotting all of the points. I just plotted these 3 up here so you can see the shape. Okay, and then the new graph. Yeah, I'm not going to make it all the way to 9. I'm only going all the way to 4 here. I'm running out of board space here. So my new graph now is 0, -2. So 0, -2, that goes here. 0, -2. 1, -1 right here. And 4, 0 right here. And there you go. It's been shifted down 2 units. For the original graph, the domain was 0 to infinity. That's the old graph. And the range was also 0 to infinity. In the new graph, the domain remains the same, but the range changes. Remember, the range is the y values. So the y values go from -2, inclusive, so it is touching -2, and it's going all the way up to infinity. When you plot this on your computer, you're going to plot the terminal point, or sometimes called the initial point, plus one of the other dots. You can just pick whichever one you like. Once you've clicked on the second dot, it's done. It won't let you click anymore. So you can plot, 4, 5, 6, 100 dots on paper, but on the computer, with the software that we're using, it's only 2 points. Okay. It's getting better, Anybody that was taking these math classes, 10 years ago or something, the programs were really primitive. So we've made a lot of progress. They've also gotten cheaper. I'm giving it to you for free on Canvas. You don't have to buy an access code or anything like that. Okay, I'm going to do more of these. I'm obviously not done with this, but I need to get through all of the different types. So let me just do a couple of each type. Next, we're going to talk about horizontal shifts. So this time I'm going to add 4. Just trying to pick a different number, but I'm going to do it inside of the absolute value bars. Okay. Now this one takes a little patience, or maybe just a little bit of acceptance of the fact that it's going to be strange. All right. Horizontal shifts are the opposite of what they look like. So the effect is it affects the x values. The effect, now this is the weird part, it shifts horizontally to the left 4 units. Yeah, left, not right. I will explain why later. I've made this mistake before where I try to explain it now and it ends up taking me 45 minutes just to explain why. All right, and so I've decided I'm not going to tell you why it's backwards right now. I'm just going to tell you it's backwards. Yeah, the effect is backwards. Yeah. So it affects the x values, but the effect is it goes the other direction, and I will explain why later when we get deeper into the subject. In fact, if I do enough of it, the explanation might just become self-evident, and you don't even need me to explain it. But you know, I have an explanation whenever we're ready for it. Okay. So let me show you what the graph of this thing would look like. So we'll start with our mother, or our parent function. I don't know about you, but you got to memorize the x's and the y's, right? I want you to know these, right? Or, I mean, obviously, you can just look them up if you have to, but if you really want to test your brain or train your brain, just memorize the x's that I told you in 3.1, and then let the y's fill themselves out, yeah? Y is the absolute value of x, so you don't have to memorize the y's. They basically memorize themselves. The absolute value of -2, you don't have to memorize that. That's 2. Absolute value of -1, that's 1. Absolute value of 0 is 0. This is a 1, it just stays 1, and 2 stays 2. I mean, you still have to know what absolute value means, but you don't really have to memorize it. You just have to know. All right, so at this time, it's going to affect the x values, and it's going to go left 4 units. So we are going to add -4 to all the x's. Notice that I said add -4. I didn't say subtract. All right. That's because the way that I subtract typically is I add the opposite. Now, if you want to subtract, that is the same as adding, but you'll probably make a mistake. I know that I would, and I do this all the time. Yeah. And so now we're going to go through the transformation. So our new table. Here, I'll just write it up here. So our new table is x and y, -6. See, that's why I like to add. -4 plus -2 is -6. I'm not kidding. If you subtract, you'll go -2 minus 4, and you'll end up getting the wrong answer. You might not. You might get it right, but you know, any little thing that you can do to give yourself an advantage, I want you to have that advantage. Unless you don't mind having a disadvantage, you can certainly fight harder and get through it, right? All right. Notice, because it's only affecting the x values, the y values are going to stay the same. So this is your new table. That's the new transform table. So the old graph kind of looks like this. I'm doing it very quickly. All right. C 3.1 lecture. You'll see me draw the graph. Yeah, I did it all very meticulously, point by point, you know, dot, 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 etc., etc. All right, I know it's not perfect, but This part really is not what I'm grading anyway. I'm only going to grade this part, the final result. All right, so the new graph, there's X, there's Y. Now this is a little bit tricky on the computer. You must plot this point first, the middle point. So keep your eyes on it. It's called the vertex. You must plot the vertex first. So -4, 0. That must be the very first point you plot. Okay. And then what you do after that, it's up to you. I'm going to do all of them, but you can just pick another point. For example, you could do -6 and 2 or something. So on your homework, you're basically done. This is what it would look like on the homework. All right. Now, I'm not using a computer. I'm using a pen and ink, whiteboard. So I'm going to plot all of them. So -5, 1 is right here. -5, 1. -3, 1 is right here. -3, 1. And then -2 and 2 is right about there. And I recommend if you're taking notes and you're doing this on paper, just plot all 5 of them. And then when you get onto the computer and you go to type them in, you can just choose whichever ones you like. Or sometimes only a certain number of them will fit on the screen. So, of course, you got to pick ones that actually fit on the screen. I will give you a general hint in this chapter. If you get all values that don't fit, all of them don't fit on the screen, then you did something wrong. All right. I've gone through these with a fine-tooth comb, so to speak, and every graph has at least 2 points that will fit on the screen nicely. Okay. Let's do another one of those. Example 4, we're using x cubed. And when I say inside, I mean inside the imaginary parentheses minus, 5. That's clearly a 5. There we go. That's what I mean by inside. I mean as if there was an invisible set of parentheses around the x. There actually is, you know that? All the mother functions have parentheses. Yeah. The square function really looks like that. The absolute value function really looks like that. Although that's kind of silly. But it's true. That's really what's happening. Yeah. The square root function really looks like that. Now the cubic function, it's the one we're doing here, looks like that. So you got to imagine the parentheses in your mind because they will not always be visible. Now what's another one? The reciprocal. Yeah, so you see a function and it doesn't have parentheses, it does. Every function has parentheses. They go around the variable. Is there one more? The cube root function looks like that. Okay. I'm just saying that because as I go through the lesson, you'll see me just all of a sudden toss in a pair of parentheses, and you might be sitting there going, where did he get the parentheses from, right? Well, they're there already. You know, you're just kind of revealing them when you do that. Okay, let's go back to affect and effect. The effect, what does it affect? It affects the x values. What is the effect? It's going to shift it horizontally 5 units to the right. Yeah, backwards. Yeah, and again, I'll explain why it's backwards later. Or maybe the explanation will just become clear as we go along. All right. So 5 units to the right. So what's our old function? Our old mother function, MF, mother function. -2, -1, 0, 1, and 2. I was thinking about whether or not that's going to fit or not. The y values, now this is the mother function, so y is equal to x cubed. It's really hard to see that. Typically, we just say x and y, okay? I don't want you to forget who y is, so I'm just bringing it down here so everybody can see who y is. When you're doing this, you can just say x, y, all right? So -2 cubed. -2 cubed is -8. I mean, you might have all these memorized. I don't know. I don't bother. I just memorize the x's, and then I let the function tell me who the y's are. You know, why memorize x and y when you can get away with just memorizing x? -1 cubed, that's -1. 0 cubed, that's 0. +1 cubed, that's 1. And then 2 cubed, that's 8. All right, now here's the weird part. 5 units to the right, so we are going to add +5 because we're going to the right. All right, add +5 to all the x's. All righty. I'm going to bring it up here so you get a nice new table. Can you guys see that? Oh, there you go. X and Y. So 5 plus -2, that's 3. I know that's a long jump right there. We can handle it. 5 plus -1, that's 4. By the way, notice I'm saying add, but what am I actually doing? 5 minus 2, yeah. Here's where you actually start adding. 5 plus 0, that's 5. 5 plus 1, that's 6. 5 plus 2, that's 7. Since it only affects the x values, the y values are going to stay the same. -8, -1, 0, 1, and 8. Okay. Since I'm not grading the original function, I'm not going to grade that anyway. It's just scratch work. You only have to graph the new function. Sometimes if I really want to be classy, I'll use this. Now here's the deal. The middle row is called the inflection point. You have to plot that first. So 1, 2, 3, 4, 5, right there. Got to plot that first. 5, 0. All right. And then I'm going to do the rest of them. All right, so what do I got? 3, -8. 1, 2, 3, 4, 5, 6, 7, -8. And 3. I'm not going to label every point. I'm just going to do it like that. So there's 3, -8. I just labeled it so you can all see that's -8. This is 3. 4, -1. So -1 and 4 right about there. 6, 1. So there's 1 and there's 6 for x. X is 6, y is 1. And then finally 7, 8. 2, 3, 4, 5, 6, 7, 8. All right, so on the homework, you're going to do the inflection point plus 1 additional of your choice. All right, the inflection point is always the middle row of the graph, of the chart, the table. We don't call it a vertex in this type of graph. We call it an inflection point. Okay, there you go. I think I didn't do domain and range on the last one. Maybe I'll do domain and range in a future one. This one is actually a free answer. If you remember, I said this earlier in chapter 3. Sometimes you can memorize the domain and range. It's -infinity to infinity for both the domain and the range. That will always be the case. Sorry, it's not a square, it's a cube. I'm glad I talked about it. That will always be the case for a cubic function. So there's no calculation or anything that's necessary for the domain and range. Okay. So we've done the vertical shifts up and down, horizontal shifts left and right. Next, reflections. Reflections are also called flipping. Yeah, or some people just say flip or flips. Okay. And in this section, we need to use the f of x notation. So suppose you have the function f of x equals, which one should we do? Let's do the square root again. I know I've already done one with the square root, but when we're talking about reflections, square roots are the best one to look at. All right. So remember, f of x is just a fancy way of saying y. If I put a negative on the outside, this reflects or flips about the x-axis. Yeah, or flip over x-axis. it affects the x values, the y values, if the negative is on the outside. Now, by the way, when we draw the graph, we typically just switch back to y. So this is often how we would write it when we draw the graph. Okay. The effect is it flips over by multiplying all the y's by -1. So we're going to take all the y values and we're going to flip them over by multiplying all the y's by -1. That's why I like to, I use the function notation to sort of illustrate it, but then when I actually graph it, I'm just going to switch this -f, I'm just going to call that y. Yeah. That way it's not, confusing as to who is the f and who is -f and all of that. Okay. Let's see an example of that. So I often will say graph by transformations. That's just a fancy way of saying make the table, do the math, and then draw the final result. All of that can just be said in 2 words, by transformations. All right, I like to switch back to y. Remember the mother function for square root. And again, I probably won't go all the way to 16, so why don't I just stop at 9? Square root, do that first. So square root of 0 is 0. Square root of 1 is 1. 4, square root becomes 2. 9, square root becomes 3. Notice we're not doing plus or minus the square root. We're doing what's called the principal square root. Otherwise, it wouldn't be a function. All right. So y equals -f of x. So that's negative the square root of x. We're going to multiply all the y's by -1. And you better use parentheses or a dot or something like that, because if you don't, if you just write a little -1 in your notes, 5 minutes later you're going to look back and you're going to think you're subtracting. The mind is a terrible thing. It will do whatever it wants to do. It has a mind of its own, so to speak. So make sure that you train your brain, put the parentheses around it so that your mind is well trained. All right, I'm going to call this the trans mathematical highway. I almost put my y on the wrong side, x and y. All right, it affected the y values. I'm looking at the wrong values. So don't change your x's. Change all the y's. 0 times -1 is still 0. 1 times -1 is -1. 2 times -1 is -2. 3 times -1 is -3. So this is called -f of x, if you like. It's the same thing as y. Oh my God. Oops. Some of you are probably screaming at your computer right now. I'm going to get extra credit. Oh, I found it. Oops. Okay, there we go. This is your original f of x, square root of x. I've been on YouTube for too long. I'm starting to lose my mind here. Okay, again, I'm not going to grade the old function or the MF, the mother function. I'm only going to graph the new function. We sometimes refer to this as the offspring. Got to keep them separated. Okay, should I use my graph board? I don't think I need to. All right, so I'm not graphing the old function. I'm only graphing the offspring. This point here is called the terminal point. Make sure you plot that one first. And then whatever you do after that, just pick another point that fits on the graph. I'm going to do all of them. So there's 1 and -1, 4 and -2, you think I could fit 9? 5, 6, 7, 8, 9. All right, there's 9. And -3. Now I'm kind of wishing I would have used the board. All right, and so here's your graph. There you go. So that is a reflection about the x-axis. And if you notice, it looks as if the graph got flipped over the x-axis. Or another way to think about it is the x-axis is like a mirror, and the mother function is looking in the mirror, and this is its reflection of the mother function, reflected about the x-axis. Well, if we can reflect over the x-axis, then we should also be able to reflect over the y-axis. Reflect, graph, same thing. So graph y equals, sorry, I got to just say it right. Given y equals the square root of x, so that's your mother function. I'm really going to beat this one up a little bit here. Or f of x equals negative square root of x, graph y equals square root of negative x by transformations. So this time the negative is on the inside of the radical. So this is your mother function. Two different ways to say it. You can say y equals, or you can say f of x equals. It really means the same thing. Okay. So graph this by transformations. So this time, it affects the x values. The effect is it flips over the y-axis. So notice, it's affecting the x values, but it's flipping over the y-axis. Oh, that drives people crazy. I can't tell you how many times I've been in the classroom and my class just goes, what's going on? I thought X, Y, I'm so confused, right? And it's going to do that by multiplying all the x's by -1. So we're going to take our mother function. I really should have just kept it out. It's the same mother function we had last time. So that's my mom. That's your parent. Yeah. And now you're going to multiply all the x's by -1. You can use parentheses, or you can use a dot, or if you really want to be safe, use both a parentheses and a dot, so it's really clear that it's been multiplying. Now take a ride on the transformation highway. -1 times 0 is still 0. -1 times 1 is -1. -1 times 4 is -4. -1 times 9 is -9. Notice it only affected the x values. It did not affect the y values. And so this is the new function, y equals the square root of -x. This is the parent. This is the offspring. You got to keep them separated. So now we're going to draw the graph. Again, I don't really need to see the graph. Don't draw the mother function. I mean, unless the problem is specifically telling you to, which I don't think will. I think that's already been passed. In this section, we're only graphing the offspring. Maybe I will use my board. What the heck? I mean, I bought this thing. I might as well use it. So here's your y. Here's your x. Okay. 0, 0, that's called the terminal point. It's where the graph either starts or where the graph ends. It really depends on how you're thinking about it. Remember, one beginning is always some other end. When one thing ends, another thing begins, and so on and so forth. I know that's deep. -1 and 1, that's right there. -4 and 2, 1, 2, 3, 4, and 2 is right there. Again, I'm just marking them with my pen. The numbers are right here, so I don't need both. It starts to get really cluttered if you give me both. I can finally fit 9 on there, in this case -9, 5, 6, 7, 8, 9. Maybe I will put it on there just for show. 9, 3. And you go like this. Okay. I didn't do the domain and range last time, so I might as well do it this time. The domain is -infinity to 0, touching 0, so it does include 0. The range is the y values from 0 to infinity. All right. So this is y is the square root of -x. One more reflection. One more reflection. It's just a reflection. Sample 6. Now, I probably said this before, but in case I haven't said it before, I have a pet peeve about mathematical, catchphrases. And one of those catchphrases I was actually taught when I was young, And I had to, get over it after many, many years because it really causes a lot of damage. You learn these things when you're little kids. And one of these phrases is 2 negatives make a positive. Oh, don't tell me that. 2 negatives do not always make a positive. If you say 2 negatives make a positive, you have to also remember there's one more word. Sometimes. Sometimes 2 negatives make a positive. What happens is when you're little, you learn these things, and then you grow up and you still think that 2 negatives make a positive. These are definitely not going to make a positive. Okay? The negative on the inside reflects about. Ever wonder why we say about face? About face means turn around. Yeah, it means turn around. Yeah, turn over, essentially, about face. So the negative on the inside reflects about the y-axis. The negative that's on the outside reflects about face, about the x-axis. Together, this is called reflecting about the origin. So we call this reflecting about the origin. The origin is 0, 0. That's the center point in the graph on the axes, the graph paper. So we're going to graph this by transformations of y equals square root of x. So we have to have a parent. You can't transform nothing. Nothing from nothing gives nothing. Nothing with nothing gives nothing. You have to start with something. You got to have something if you want to form a transformation. You got to have a seed. Let's do it. All right, so the parent is, probably have this memorized by now. X goes on the left, Y goes on the right. Notice I've been doing this for 30 years and I still sometimes screw this up. So you gotta police your, keep your eye on your own mind. Keep your mind in check. Check your head. All right, the parent, 0 is 0, 1 is 1, 4 is 2, and 9 is 3 because we're doing the square root. All right, we are going to do both. Yeah. Now this is the weird part. Reflecting about the y-axis, you actually do to the x's. How? Why? Why does it have to be so confusing? Well, just think about it for a second. If you multiply an x, look what happened in the last one. If you multiply an x, it flips it over the y. So if you multiply a y, it flips it over the x. I don't know if you've noticed, but reflections are always backwards. My hat, you can read my hat. Yeah, but if I were to go to the bathroom and look in the mirror, these words on my hat, stay human, would be backwards. Okay? By the way, this is the motto for our current times right now. So if you wonder why I wear this hat every day, because we all need to be reminded. Stay human. Okay. Transform. So this is my f of x. The problem said it was called f, so I'm going to call it f. If the problem said it was called g, then I would call it g. If you want to be lazy, you can just call this y. It's okay. Then nobody's going to care. Right? You're going to get the right answer. The function's not going to be, offended that you didn't call it by its name. All right. And so now we're transforming All of the x's are getting multiplied by -1. That's very easy. You multiply by -1, it just flips the numbers over, makes them their opposites. The only exception to that is 0. There's no such thing as -0. So, but all the other values will get flipped. Okay. And so this is our new graph, or our new table of values, which we can now graph. Okay. Now, sometimes I go farther than -9, but I think on this graph, I'm just going to -9. So 0, 0, that's your terminal point. -1, -1, that's my next point. If you're lazy, you're done now. You'll just connect them. Just don't make it a straight line, okay? It's not a straight line, it's a curve. I'm going to go ahead and draw all of the points, and that way it clearly curves. And then -9 is over here, and -3. And there you go. There's your graph. I don't always ask for domain and range, but I try to ask enough that by the end of this lesson, you should be pretty good at it. If there's ones that I missed or I just intentionally or unintentionally skipped, then we can, we'll probably see those again. The domain is all the x values, so -infinity to 0. Look at the x values. Yeah, this is -infinity over here, all the way to 0, close bracket. The range is the y values. This is -infinity. It's going down to -infinity. And it's going all the way up to 0. So in this one, the domain and range are both the same. Whew, that's a lot of reflecting, huh? I wish I could say we're done, but we're not. We're going to do more reflecting in part 2 of this lesson. So I'm going to have to do a part 2. I want to end this part 1 with the scaling. That'll at least have done all the transformations. And then in part 2, we'll put it all together, and I'll give you problems that basically have a mix of all the different types of transformations. So finally, we have scaling. Scaling is like what you do on your phone when you put your fingers on the screen and you go like this, when you stretch out the screen, or maybe you shrink something down. So this is stretching or compressing. Yeah, compress means the same thing as shrink. Okay. Now, there are 2 types of scaling in the universe, in the world of mathematics. For Math 10, we're only going to do vertical. So these always affect the y values. All right. We use the letter C for constant. Scalar, I know I wish we could use S for scalar, but we use C. Well, there's a C in the word scaling. Constant, yeah. In front of the function. In the front, I mean on the left, outside. So if you have a function like this, you're going to put the C right here out in front of the function. All right. Typically, we omit the dot. Not always, but we often omit the dot. Because if I just say CF, that means the same thing as C times F. So there you have it. We've been doing that since you first learned basic algebra, right? So this is equal to a vertical stretch have two T's? Stretch. I think so. S-T-E-R-E-T-C-H. Or is it just stretch? I don't know. I think I like the second T. Vertical stretch by a factor of C. If C is greater than 1. It's a vertical shrink or compression, also known as a shrink. You know, us math people, we're never happy with only having one word for something. I want to have a dozen words that all mean the same thing. By a factor of C, if C is between 0 and 1. And then I will just make a little note down here. If C is 1, it's invisible. So we would do nothing. Yeah. So C, the constant, will always either be greater than 1 or it will be somewhere between 0 and 1. All right. And so these are the effects. There are two possible effects. There's only one affect. It affects the y values. All right. And it does it by stretching it vertically if it's greater than 1, or shrinking it if it's less than 1. And that's exactly what happens on your phone when you go like that with your fingers, or sometimes there'll be a little plus sign or a minus sign and make it larger or make it smaller. I think I'm up to 8. I'm not sure if I got off number or not, but I'm going to go ahead and do 8. Is there a function we haven't done yet? Let's do, let's say, y equals 2 times the cube root of x by transformations of f of x equals the cube root of x. So again, we're always starting with a mother function, so we're transforming the mother function. That's our mother, that's our f. This is mom. Yeah, mom is the f of x. Or you could just call it y, same thing. So you could just say cy. Yeah. In these problems, I like to use the function notation. All right. So notice this is f right here. So this is 2f of x. So in this case, c is 2. So that means it's going to be a vertical stretch by a factor of 2 because 2 is greater than 1. So we're not doing a shrink. We're doing a stretch. I need a table. Yeah, I need a table. This has taken up a lot of my space here, so I'm going to go ahead and get rid of this. So here's my mother table. Again, if you like, you can just call it x and y. You don't really have to call it f. This is the same thing as y. So this really means 2y, or 2 times y. These all mean the same thing. Tomato, tomato, tomate. We're using the cube root mother function. So that is -8, -1, 0, 1, and 8. Remember, the cube root is the inverse. I haven't really defined that term yet, but you could just say reverse. Just reverse the x's and y's from the one we did a minute ago, or several minutes ago, the cube root, the cubic. This is the cube root. So the cube root of -8 is -2. The cube root of -1 is -1. The cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. And so now we are going to multiply all of the y's by 2. All of the y values by 2. That is our trans. That's our transformation. Before I do it, I just want to make something very clear. See, xy, xy, that's one of the reasons why we like to use f, because f tells you which one is the mother and which one is the offspring. But the problem is sometimes the offspring has the same name as the mother, or sometimes we switch to a totally different letter like G. I'll probably do that in part 2 of this video, of this section of the lecture. In this section, I'm just using x and y and f, all right, just to keep it simple. So I got -8, -1, 0, 1, and 8. I have not affected the x values at all. I have affected only the y values. So this is your new graph. This is 2 cube root of x. Notice the 2 is a big 2. That's a scalar. The 3 is a little 3. That's called an index. I just have to say this because I want you to know the words. All right, and if you really like, you can put a dot right there so that it's very clear. You know, you are multiplying these things together. Multiply by 2, or whatever the scalar happens to be. Ready? Set. Graph. Again, I'm only graphing the offspring. I'm not graphing the mother function. I'm going to go ahead and mark off the 8s and the -8 so I don't get confused. 4, 5, 6, 7, 8. It's good to know, where you are. Okay, start in the center. This is called the inflection point. Inflection point, PT for point. Put that point first. All right, and then after that, I don't care what you do next. All right, I'm just going to do all of them. So -8, -4. So I'm going to go down 4 and left 8. -1, -2. That's down 2, left 1. Right there. I already got 0, 0. 1, 2, so just go up 2 and over 1 right there. I don't really want to put the 1 here. It'll get too messy. All right. And then 8, 4. I've already got the 8. There's the 4. So 8, 4 is right there. And there you go. This is another free domain and range if you like. I might as well give it to you. Remember, cubics and cube roots have free domain and range answers. That's not a bad deal. If I put this on the test or on the quiz, you get free answers. Domain, as long as you remember which ones are free. Cubics and cube roots, free all day long. Yeah. The rest of them are not free. You're going to have to know them. You're going to have to work them out, and I'll do more of that in part 2 of this video. And I don't know, this might be example 9. I might have got off count. I'm really getting tired. I've been on YouTube all day. So I'm going to try to get one more in. One more. Shrink. Compress. The only one I haven't done today is reciprocal, right? I've done quadratics. I'm going to end off with a quadratic. I like to start and end with quadratics. I did square roots. I did cube roots. I did cubics. I think I did one absolute value. Did I do an absolute value? I think I did. If not, we're going to do more. The only one we haven't done today is the reciprocals. Those ones take special handling. They require a special permit, special extra postage. So we'll save those for the next one. So this is 1/2 x squared by transformations. Transforming f of x equals x squared. Right, so here's your c. That's your scalar. So we're going to multiply all the y's by 1/2. Yeah, the effect is it compresses by a factor of 1/2. It's going to get half. It's going to become half of its original height. The effect is it affects the y values. All right. Let's start with our mother table. This is your mother table. It's the same one we started this video with. You probably have it memorized by now. And you're going to multiply all of the y's by a factor of 1/2. Or if you prefer, you can just divide by 2. That's the same thing as multiplying by 1/2. So you get 4 times 1/2, that's 2. Notice the x's are not changing. They're going to be the same. 1 times 1/2, that's just going to be 1/2. 0 times 1/2, that's still 0. 1 times 1/2 is 1/2 again. And then 4 times 1/2 is 2 again. So this is the new offspring table. It's been compressed or shrunk by a factor of 1/2. In the next video, we'll put all this together. I want to just wrap this up now. So what do we got here? Sometimes it is kind of neat to see the mother function and the offspring kind of in the same photo or in the same graph. If you want to do that on your own, just to kind of get an idea of it, maybe I'll illustrate it one time here since I'm at the very end. I think I can afford to be a little bit messy. So here, let's do the new one in red. So remember, do the vertex first. The vertex is always the middle row. So do that first. And then you're going to go, I would just do this point, -2 and 2. And then I'm going to do this point, 2 and 2. The fractions are not that easy to get because you're going to have to click in the middle of a cell. So these fractional ones on your homework, I would just avoid them. I don't know. I mean, I'm only saying this to just make your life a little bit easier. There are some of the graphs that will allow you to click right in the middle and make a half. But they don't all do that. And I don't want you to be frustrated going, it's not clicking, and send me emails saying it's not clicking. So just avoid them. But on paper, I can do them. So that is the new graph. Yeah. And if you want to see what the mother graph looked like, or the parent, that's the old graph. Just look at this original table here. Yeah, this is the old graph before you multiplied it. So not doing that multiplying by a half yet. And you can see what it looks like. You get 0, 0, you get 1, 1, and then you get 2 and 4. And that's the old graph. So sometimes it's useful to see the old and the new, in the same picture, and then you can see how they've changed. The new graph is half the height of the old graph. All the y values, as you go out, the y values will always be half of whatever their parents' y values are. Be like having a child that was always exactly your height. So as you grew, they grew, but they always remained half your height. I know that doesn't happen with people, but it does happen with mathematics. Okay. You're really earning your points for this one here. I'm all out of things to say, so until we meet again, this is Dr. Jordan. I will see you on the internet.